I'll just tell you a little bit about myself.
Mhm.
So I am obviously a structural engineer with WJE, and we can talk a little bit more about what WJE is, but I'll tell you a little bit about my background. So, I grew up in the Chicago area, and then I went to school at University of Illinois. I had no intention to start with civil engineering. My father technically has a degree in civil engineering from Clarkson. Do you know Clarkson in it's up in northern New York? It's
No.
way north, like almost to Canada, but in New York.
Oh, okay.
Yeah. Okay. And so I had no intention. Then I didn't like the major I was in. My dad said, you should try civil engineering. And I was like, when you're young, you don't want to do what your parents say. And so I did it. And I ended up loving it. And I was really good at school, but I never knew really what I wanted to do afterwards. Like I had one internship and I didn't really like it that much. And I think now I look back and it was probably the internship, not what I was doing. And so I just kept going with school because I was good at school. And so I went through and ended up, after undergrad, went to University of Michigan, and ended up with a PhD, and then thought, well, maybe I should be a professor, right? And so got a professorship in Louisiana, at a smaller school there. And then after 2 years, I moved to the University of Kansas, and I was there for 3 years. And just wasn't ever fully satisfied with my career path. And then I changed to WJE for two reasons. One, for family reasons. My wife is from here in Florida originally.
Oh.
So we were able to get to where we wanted to be. And then at the same time, I wasn't super happy with being a professor. And so I found this, and I've actually really, really enjoyed it. It's been a lot of fun. It's very different than what I did in the past. Very different than university, very different than professor, but not as different as you would expect, to be honest. But it's just different in a lot of ways. But it's really, really enjoyable. And so, that's a little bit of my background. So here at WJE, I've done a lot of different projects, and it's really opened my eyes up to a lot of things that I had not really have seen or noticed in the realm of engineering as an academic or a researcher, right? And so when I was in graduate school, my research, obviously you read the paper on steel tubes, right? So
Yep.
My research was on steel tubes. I also did a lot on steel floor systems, a lot of steel.
Actually, I have some question regarding that if you don't mind answering later.
Yeah. Let's get to that. We'll get to that. Absolutely.
Yeah.
And then, so the steel floor system, all sorts of steel related things, and some material related things here and there. And then a little bit I started right at the end, right before I left, I got into some wind and fatigue issues. And that was really good because I moved to Florida. And as you know, Florida is very susceptible to hurricanes and those sorts of wind issues. And so you start learning about that. But the one thing I never realized in my trip to here is how much what you might not consider part of the structure, like not part of the main wind force resisting system or the lateral system, but like things like windows and cladding and facade elements are structural in a sense, right? We have to design these elements to remain on the structure. Sometimes it's easier than a big high-rise structure design, obviously, but sometimes it's really complex and it can be really challenging in terms of what we kind of have to deal with in terms of that. And so like here in Florida, obviously the windows and doors and facades are a huge issue. There's a lot of rules about it, a lot of different ways it's done than New York, for instance. And so it becomes quite challenging. And so that's just, something to keep your eyes open to, right? And I just wanted to make that point really quick, is that one of the big things that I never realized was how much and diverse structural engineering or any sort of civil engineering where structure is involved can be. And there's some really interesting things in the stuff that you might not learn in class super well, that you can apply your basic principles to all the time. And so when I was a professor and when I talk to work with my interns now, or any sort of young engineer maybe who's going back to graduate school or something like that, that is where I get on, basics, fundamentals, right? Because you can apply them to anything. Like I know a lot about mechanics, right? So now, I mean, the way that loads transfer through like a window is quite complex and confusing, but it's not that hard once you know mechanics and you kind of see how the system works, right? So that's the point. So that's just my background. Yeah, I mean, there's certain jobs, right, that are going to be a lot of field work, right? And that's just the nature of them. And then there's jobs that aren't, where you're doing a lot of design. For instance, my wife actually is an engineer at Thornton Tomasetti.
Oh.
Yeah. And so, yeah, I mean, she doesn't ever go to the field, like maybe once every 2 months or something, right? And I'm very different. Well, COVID has changed it a bit, just because of our family and whatnot. But typically before that, I was in the field pretty much every week, at least a few days a week, or if not more. We'd have times where it'd be like 2 weeks in the field and a week in the office, stuff like that. But yeah, definitely different jobs will have that, and great. And then what, are you going to do research for your master's, or is this coursework?
Just coursework, unfortunately, but yeah. If I decide to pursue a PhD.
Did you have that thought in your mind to do a PhD?
I actually took the GRE in case if I ever want.
Okay, that's so they didn't make you take it to do graduate school at Cooper Union, but you took it in case.
Yeah, I took it in case.
And you feel like it's something well, you think about it, and if your GRE score, it's not everything. I never even, when I was a professor, I just looked for a minimum number, and it wasn't even a high one. It was just some low value. And then they changed all the numbering and I didn't really understand it. And I just said, what's the percentile? And I was like, yeah, that's fine. Because the test is, it's really just not a great indicator of how you'll perform in graduate school. I'm more interested in your grades in class. When I was looking at students, I'd be like, okay, here are the grades and they're good. And are they involved? Were they taking, it just shows commitment, right? Cause I feel in my mind, this was my mind, right? A lot of people can take the GRE and do very well and they're just naturally good at it, but doesn't mean they're committed to the major or to what they're doing. They just did well and, could get lost really quickly. And then there's the other side of it where it's they're hard workers. They're smart because they're getting good grades. You can be a hard worker and not smart, right? And not get good grades. But you get hard worker, smart, you're getting very good grades and you're involved. Okay, that's the kind of, so whatever you got on it, just keep that in mind. Those other things are, faculty are looking at those other things, right? They're not just concerned with your number.
I also heard letter of recommendations also very important.
Huge. Yeah. I mean, I'm fairly certain that it's one of the bigger things that especially if I know the person who's recommending, right? If for instance, I recommended one of my former students to Michigan, to my advisor and some of the other faculty there, and it went very well for her, right? because like they know me, they know who I am, they know what I'm doing, you know, et cetera. And the great thing is now that same student, she's working at WJE in the Chicago office. So it's awesome. It kind of full circle. She was my student. I recommended her to Michigan.
And now you guys work together.
Now she's back to, I said, you should hire this person in our office. And they ended up hiring her, and she's doing great. So, you know, that's yes, it's huge, definitely huge. And then making those connections. That's why research as like a master's student, if you want to do PhD, or even as an undergrad, like if you want to get into that sort of research realm, that's, I think, really important. I did undergraduate research. I'm pretty sure that's why I got into school. I had a very good couple recommendations from faculty. It wasn't just he was in my class or she was in my class kind of recommendation. And so that was helpful. I'm very certain of that.
So did you start the HSS to HSS mobile frame system in undergrad, or that's your like PhD?
Yeah, that's funny. I don't know how to turn this off. It's fine. So I started in undergrad. I was doing research on cement composites with fiber. And so when I applied to Michigan, I applied and I got asked to come work for a research group doing very similar things. So there's a research group there that's doing, they call it engineered cementitious composites. And so I went and worked in that research group for a year. And I was on fellowship, which means I was it's a kind of a really nice way to get paid, right? Because you can kind of do whatever you want to do. And so I found I was somewhat interested in it, but it wasn't exactly for me. But the interesting thing is the summer between undergrad and graduate school, I was an intern at AISC, so the American Institute of Steel Construction, you know, the big book, right? I interned at I interned there for their engineering department. And so that was really just a great internship. I learned so much. I made so many connections of people and whatnot. And so what I ended up doing then is I decided, no, I kind of want to do something related to steel, like after a year. Actually, after 9 months, it was after the school year, essentially. And so I changed advisors to a very new faculty. I was his first student doing PhD. And so Jason McCormick is the advisor I had. And you see his name on those papers, right? And then he and I ended up talking to some of the research people at AISC, like talking and seeing what their needs were. And then he got some funding. And then mostly it was him after that, right? And I was just doing the research, but getting funding. And I went and started doing work on steel tubes. It's an area that's it's a bit confusing. The design of it isn't as straightforward. I guess let me take that back. It's not straightforward. It's not taught in school very much. And so I feel like if everyone learned about steel tubes and then we came and said, okay, now you have to design wide flanges, they'd be like, that's confusing, right? But it's just you're just not exposed to it as much. And so it's a bit more confusing for people to do and design. And there's some unknowns. There's less research out there on it. And so our question was, you know, are we missing something with steel tubes in terms of behavior or performance that we could gain compared to wide flange sections, right? So actually in Asia, especially Japan, and I think in China as well, super common to use steel tubes for columns. They're just really common. Our question was okay, we know that in the US, it's not very common at all to use a steel tube as a column, although it's common to use them as posts, in buildings, in warehouse buildings and all sorts of things, but not as a column in a 20-story building or something like that.
Yeah, or just like the bracing near like, you know, staircase for framing.
Yeah, definitely used for brace frame systems, but built into built into a wide flange column system, right?
Yep.
So we thought, well, is there something there we're missing? Could there be some behavior or performance increase that would be beneficial? And because there are some nice things about it, right? They're braced, the flanges and the webs are all braced, right? Instead of you have unbraced flanges on a wide flange, so you get a little bit lower B over T ratios on it, which means you're more susceptible to some buckling issues. There's some nuances to that because steel tube is only made in certain sizes, so it has some nuance, but and it's a bit thinner than getting a 1-inch thick steel tube is possible, but it's not common. And then the other thing is that it doesn't have any lateral torsional buckling, really any issues with that. It's so torsionally rigid that for most lengths, you don't really have any issue related to lateral torsional buckling. And so we thought, let's see if, what the benefits are, how you would connect these. Could we make a moment connection with steel tubes? Do steel tubes have the cyclic performance that they need to be in a seismic system? And we kind of went through that questioning, and so we did that through both experimental studies. So there was kind of 2 rounds of experimental studies. The first one was just the tubes themselves and looking at the cyclic performance of the tube, getting it to understanding the plastic hinge behavior of the tube itself. And then the second study was an actual moment connections. And so I think I had in my thesis, I probably had 2 by the time I left. I left to go teach right before the last test, and I think there was 2 or 3 in my thesis, and there was a 4th, and I think there were 4 total, 3 or 4 total. I can't even remember. It's been it all blends together, right? It's been I graduated 2013, so it's been 7 years since I did that, and so the papers have been coming out. They came out. I think everything has been out for the last couple of years now, at least. But yeah, and so we learned a lot about that behavior. And so Professor McCormick has now taken that to kind of the next steps, right? So he's looking into different types of connections, more in depth about the behavior of the connections, fracture behavior of the connections, and just trying to understand that and be he's helping the steel tube industry, but he's helping people understand the behavior of steel tubes and the usefulness of those in the US, essentially. There's another faculty member in Canada and at the University of Toronto who's also very, very into that, and that Jeff Packer, also a very good researcher as well. And so they're working together on that. And slowly these things are not what I did, right? But like steel tube work is getting applied to the code a little bit and updating the code. So one of the interesting things, because of the work that's been done by those researchers, especially Dr. Packer, there used to be Chapter K, and there still is a Chapter K in the steel specification, but slowly they've gotten the tubes, and Chapter K focused on steel tubes only. Let's just to make it clear. Slowly we've gotten steel tubes into Chapter J, which is the just regular connections or joints chapter. And so, it is slowly they're advocating and getting people to understand tubes are just the same, but a little different, which is a good thing. So yeah, that was my PhD essentially. And during my PhD, I did do a lot of finite element modeling as well. And so a lot of working in Abacus. And so I still do that to this day, use Abacus as a software to help me in a lot of different situations. And so it's been really, really a useful tool, actually, really useful. And I still do to this day a lot of experimental studies. I've done big ones. And so all of that background I learned, right, has been like really, really excellent in terms of I was able to, jump in an experimental study with no big issue at all. It's, even though it's a totally different topic, there was some wind tunnel testing here. right? Like I had that background. And then the modeling stuff, like I've had some stuff come up recently for some windows, and we're wondering about the stresses that are in the windows. And I was able to use my modeling background to model the glazing, so the glass itself, and put it under some different temperature changes and see what stresses were induced in the glass layers. And so that's why that's why I say the basics are the basics, right? Once you kind of understand that, that's the really important part. So, yeah. Do you have any questions or anything you want to ask me, and specifically, I guess? Ooh, geez. Other than about that, or I can answer more questions about steel. I can talk about steel tubes all day long if you want to. Whatever you want to know.
Actually, I want to have a few questions regarding the paper, and then perhaps I want to,
Which paper that you read? Which one was it?
It's the welded HSS to HSS movement connection for the seismic application.
Yeah. Wow.
Well, it's some general questions, so you don't have to refresh your memory on the paper. I know you guys compared the HSS to HSS versus the HSS to wide flange, but then is there any cost comparison?
That's not my forte. So definitely steel tube can be more expensive. It's just not as widely available. It's not rolled in the same way. So the manufacturing process for steel tube is just, so there's that. But then there's the other side of it where there's things that you don't need to do for steel tube that you would need to do for a wide flange that could end up labor costs. So we never did a really hard cost analysis, a cost benefit analysis of what a tube frame system would cost versus a wide flange, to tube, or we just never got that in depth in cost. It wasn't the issue, right? And I think as researchers, it's not always, we have some thought about cost in the back of our head sometimes, but it's not always the driving factor, right? Obviously, we're not going to make steel tube out of gold, right? We're like gold tubes, right? Because it just doesn't make sense, right? It's number one, the cost. Number two, the material properties don't work right. We have to think sometimes in kind of the scaling of how these things would happen if, let's say, the tubes are adopted widely and used all the time, right? Or there's some sort of design issue that is taken away from this use of steel tube, right? That could, hence one of the big ones was the lateral torsional buckling issue, right? Mm-hmm. You don't need to brace the compression flange or the tension flange of any of these tube members by code. There's technically you probably should, but the code doesn't really require any of that. And so that could really reduce the ability or the cost associated with those sort of issues, right? And so there's one cost benefit, but then there's the downside of all the connections are a little bit complicated. Okay, so it takes a little more time to fabricate. Well, maybe some of the materials are lighter. Okay, so it's less steel material, so that's cheaper. But we didn't go down that road, but it's definitely something that an owner, when they're building a structure, would need to consider if they wanted to employ the use of tubes, right? Mm-hmm. Yeah. So I hope does that answer the question?
Yep.
Okay, good question.
Yeah. Last one.
Last one? No, that's okay.
Last one regarding this paper as for now. Good. So I saw welding was used to connect, but then did you guys consider using bolting? Because what we learned in school is bolt is much better when it's when encounter seismic load or stuff, but is there a particular reason you guys using welding, or did you guys consider using bolting?
Yeah, so I'll answer that. So there are benefits. Okay, so you kind of mentioned bolting and seismic. So bolting, there are some benefits to using bolts, but there are also some benefits to using welds for seismic loads. And so, you know, but we considered welding only in this case because of the fact that this was kind of a newer research project. Bolting is quite complicated with steel tube, and it's an issue, one of the major drawbacks of steel tube. And that the reason for that is there's no way to really access the backside of the bolt, right? If you put a bolt hole through a tube, right, you can't, how do you tighten it, right? Like it,
I see.
right? And a through bolt is not a very good bolt condition. Like the way that bolts need to be applied is that the bolt should be tightened against, they call the faying surfaces. So there's the surfaces that, you know, 1, 2, or 3 surfaces should be tightly pulled together. So putting it through the tube like a through bolt just doesn't work well. It doesn't get enough tension in it, the bolt, and it's just not gripping quite tightly enough. And so, you know, the way to kind of start a problem, right, is let's look at the basics first, right? We know we can do all welded moment connections. That's not a big deal. And we know that some of those connections that I worked on could be converted to some of the bolted connections, right? Especially the ones with the collars or the diaphragms that are, you know, external or internal. You know, they're all external, internal, right? What we could do is on that outer diaphragm piece, right, is add some plates that are shop welded in with bolt holes, right? And then that bolt, and then have holes in the diaphragms that are attached to the columns as well, and then bolt them on in the field, right? So essentially it'd be just a little bit of different operation. And so that's doable. But, you know, that's just another level of complication that we weren't interested in understanding at a time, and saving that kind of for the next steps, right? We really wanted to answer the fundamental question of, you know, how do these connections behave under seismic loading conditions? And so avoiding the bolting question is just, right, like when it's the scientific method, right? You just have to step back to that, right? Like we have a hypothesis and we think about how something's gonna happen, right? And we're about it, we research it, and then we have all these factors we want to, you know, variables that we need to consider. We have to have controls, right? And and I'll tell you, in civil engineering and engineering as a whole, and I'm sure in science too, doing the scientific method is an imperfect practice always, right? Because you can never control everything. And so, and especially engineering, I would think, that's my thought there. Maybe I'm wrong, but I'm not a scientist in that way. I'm an engineer, right? But like, you have no idea of the exact material properties. You have no idea of the weld properties. You don't have everything perfectly characterized with the welds, nor will the welds be laid down perfectly, right? Right. So there's all these like unknowns, right? Like you have to just limit yourself at a certain point, like of what we can answer and understand well at this time. And so that's what we decided. That was it. So I don't know if I don't think Jason's got into, so Jason, Dr. McCormick, has gotten into any more bolted connections with these. I don't think he has, actually. I think it's kind of, I think they did some stuff with collars where you have collars wrapping around the column and you slide in and then weld quickly. And that seems pretty effective. So they're just thinking about some different ways to use welded connections. Bolting is tough with tube. I'm not gonna lie, it's a challenge. So, yeah, good question though. Any more?
Very interesting paper.
Yeah.
I really learned a lot from it. Like,
good.
I personally like had some experience with HSS like during my internship, but like I mentioned, it's for like the bracing. It's used as a bracing with like the white flange. Okay. And then in my undergrad senior project, actually, like my team actually used HSS as the truss frame.
Great.
So it's like, but then it's only one floor, and it's the project we set it in New York City, so you know, not that much seismic consideration. So it's good that I read your paper and learned a lot from it.
Good.
Kind of overwhelming, but then it's good.
Good. I'm glad that you were able to learn from it. That's good. Yeah, there's several papers out there by Dr. McCormick that would be useful for you to look at, as well as Dr. Packer if you get more interested in HSS and understanding behavior. So that's really important. So that's just something to consider.
Yep. Actually, I want to learn more from you with like new projects. So
Yeah.
is there any like project that's that you worked on in the GE or WGE that you are okay to share?
Yeah, absolutely. So there's plenty that are open to share. That don't worry. So I think one of the there's a lot of cool projects I've worked on. I've been involved in I'll just let me just start with the types of projects I've worked on. I've worked on projects in the bridge world, helping with some erection design of that. I've worked on projects in the building world in terms of fixing structural elements or rehabilitating structural elements, both for concrete and steel design, as well as looking at some failures, so like some large failures of steel buildings. I've been involved in a lot of window and related kind of structural issues. So like looking at windows for structural damage, or looking at some certain window types during their fabrication process, and looking at how the stresses are involved in them. I kind of alluded to that earlier, as well as a lot of work in the hurricane sector right now, because like that's where I live, right? So learning a lot about hurricanes and wind loads and how they affect structures, both from what we call the main wind force resisting system, as well as the components and cladding. So the windows, the doors, the facade, the roof. And I don't know much about roofing elements other than how to apply loads, essentially. So there's, those are kind of the different projects. That's just a smattering. Like there's so much more. Like it's all sorts of. It was funny when I started. When I moved to Florida. I literally in three weeks had like 3 people that had their a car hit their building, or like drove into their building, and I had to go like look at these car hit and I haven't had a car hit a building since. So like it's interesting. The thing to note is, some projects are really small and some are big, right? And so one of the biggest projects that's been really, really interesting that we did was some wind tunnel testing on sliding glass doors and windows and facade elements. And so we actually, we were requested to do this. And so what we ended up doing is we actually we bought sliding glass windows and doors and put them into a frame. And we tested them full scale at the Wall of Wind at Florida International University. If you haven't looked that up, Google that after we get off the call and look up Wall of Wind. And it's this massive open wind tunnel in Miami. And we were able to test these windows and doors under like dynamic loads, from a wind tunnel, up to like 150 miles per hour, which is like nearly a Category 5 storm. It's sustained, so just hitting it, which is extremely strong and extremely catastrophic sort of storm. Like it's just not. It's that sort of storm would be horribly damaging to any place that got hit. For instance, Dorian last year was a Category 5 storm and horribly catastrophic to the Bahamas. Thankfully, stayed off of the coast of Florida and never hit. So that was one of the big things, and so that involved. That was over about a year and a half ago now. That involved about a team of 15 to 20 WJE people. Working that we actually constructed the specimens at the lab in Chicago. So we have our own structures lab in Chicago area. and we shipped them down to the lab here at Florida International University. And we used, then we installed the windows and doors into the specimens that we bought from here in Florida. As well, actually, one other thing we did was we wanted to understand the behavior of some older windows and doors. And so what we did was actually find old profiles. So like every window and door is typically down here is out of extruded aluminum. You can have other materials, but it's really common to use extruded aluminum. And so we had aluminum extrusions actually made in China, shipped to the US, where we fabricated the window that they no longer make. Typically, most of the windows and doors down here in Florida are made in South America. So we'll glaze them or make fabricate them here, but all the extrusions are made in South America. So in Colombia or whatnot, are some of the bigger extruders of the aluminum. And so, right, and so we ran these tests. It was a really, really interesting project. I was the manager of that project. It was like doing a couple PhDs for people in 3 months. It was so fast. It's very different than the academic world where research can take a lot of time. Our client needed an answer quickly. And so we had to get that answer very quickly. The other thing we did was test some glass handrails, right? So on balconies and stuff, people like to put glass instead of steel guardrails. And so this building had that. That we were trying to mimic a building that had that. And the interesting thing that came from that is that we actually, just due to time constraints, we used another wind tunnel up in Canada. And so we all flew up to just outside of Toronto, used their wind tunnel and looked at the behavior of these guardrails. And that was more interesting because the windows, I have to tell you, even under 150 mile per hour load, they don't move very much. But the sliding glass, the handrails, when it's 150 miles per hour applied to these things, it is quite scary looking. And so that is one of the biggest, most interesting projects that we've worked on. And so I did that. Probably that was a 6 or 8 month project that I did pretty much when I moved to Florida, to be honest, right since then. And then since then, I've done a lot of work for insurance companies. So one of the big things is because I now have a really good understanding of how windows and doors behave, right, under hurricane loads. I'm able to help insurance companies with understanding claims that are being made on windows and doors around Florida. And so I've helped them with those sort of things. So, work I never actually imagined I would do, right? I didn't know that it was a thing that people did. I just thought structural engineers design buildings or fix buildings, right? But we also can help, other industries understand the performance of things that they potentially insured or worked on or dealt with. So we do that sort of stuff. And so that's one of the big areas that I've done. And it's really fun because we pull together big teams and we come inspect things, and then we'll analyze lots of data. We'll collect tons of data. We'll analyze it. So we're doing tons, there's certain parts of it that are boring, just like any part of life, right? And then there's parts of it that are really interesting, right? Have all this data, we're analyzing it, we're trying to understand it. What does this mean about how, the structure? We do this for both, windows and doors and structures themselves. We take tons of data and then we do a lot of analysis and write reports on it. That's one of the big things. And then the other big thing is, once we do all that, and it doesn't happen that way every time, right? But sometimes, it turns into how do we fix it and how do we design the fix? And with all that data and understanding, it makes us a lot more, because it hones our fix, right? We don't need to just develop. We don't need to be super conservative. We know what we're doing. We get what the behavior should be, and we don't need to be super, because we've taken so much information. And so that's kind of one of our big things here. So
actually, one question.
yeah.
Like, I'm wondering, how do you simplify all the data and then convey into like a, simplify into a report to the insurance company and
Yeah,
to them?
honestly, that's a great question. That's one of the biggest challenges of that job, the job, right? Like, so taking all this information and helping an insurance company understand, and the client understand what this means, right? So it's like, trying to get a person in Calc 1 to understand DiffyQ, right? Right? Like, it's tough. It's a challenge, and that's where you cannot let up on your writing skills, like where writing skills become extremely important, where your communication skills become, indispensable. You have to have them. You have to understand how to get these things. And I am so thankful for my time as a faculty member where I'm working and teaching people these things, because it's been a lot of practice, right? To be able to say to a client, like, this is how it works, right? Like, look, or just help them visualize things quickly and effectively, right? And so that's kind of one of the biggest challenges. That's a great question. That's a hard question. That's like, it's not like where I'm designing something for an architect, which I am doing right now. Like, I'm helping an architect design a building right now, right? Working as a structural engineer for them. So we do that sort of stuff limitedly, where I'm working for an architect. And like, yeah, I have to explain to an architect certain things, but like, he gets most of it or she gets most of it. Like, so it's not really, that's not the issue, right? Right. It's yeah. He's like at least in Calc 3, right? And you're in DiffyQ, right? So he kind of is like almost there. And so it's getting the Calc 1 person to understand. That's the tough one. Agreed. That's a great question. I think you got a good answer there, right? It's communication in your writing. It's huge. Like, it's really, really huge. It takes a lot of practice to become a good writer too. Is what I found out, and don't expect it to come right away. And when you work with people and they don't appreciate your writing, like, or I say bleed on it with red ink, right? Take that and learn from it. That's the best opportunity you have to learn. Don't feel hurt by any of that. That is just learning opportunity right there. Especially if you know they're a good writer and they're successful at that. So there's that. Let me think of. Find another project I can tell you about. I mean, I can tell you about lots of projects. Let me find another project I think would be interesting to tell you about. I think one of the cool ones that I've done recently is, and this is a little outside. I'm not in the bridge world at all, right? And I'm not very good at things like SAP, like modeling software, other than like the finite element stuff like Abacus. I'm not really a software guy. But recently I've been helping out with a group who's having some questions about some of the erection procedures for a bridge. And so I got to come in and help go through the design of the erection procedure of the bridge and help them with understanding the model after they're looking at the model, and working through that sort of exercise. And so essentially we get hired by the erector to be their engineer on that erection of the bridge. And really,
so I assume it's a new construction?
Yeah, new construction.
Okay.
Yep. And so really enlightening, like, it's a curved steel tub girder system. Oh. Yeah. And so just really interesting to see, really interesting to learn about. I understood a lot of it, but not all of it as I got going. And I would talk with people and they would show me, okay, here's how. I talked with an expert who's done a lot of bridge erection stuff, and here's how the model should look, and here's what we need to consider. And so I walked through that, and part of it was they needed me to sign off of it because I was licensed in the state they needed a stamp on, right? And so they needed me to get involved without them having to go get that stamp themselves. But I mean, I'm highly qualified for it, right? Like I had the background for it, and I had the team behind me that you know showed me and showed me what the industry standards are, right? And so you know, got to learn just a ton about it in a quick period of time. Um, and so that was really cool from a you know, structural standpoint. Also done some work on vibrations in buildings and helping with design. Like you get actually in New York City, to be honest, you get a new building, right? And they're concerned about like you're doing a build out, right? And you're helping an architect with the build out. They want to change some things up in the structural system in one of the high rises there, you know, not just on the floor level. And so what happens is you have some issue potentially where you've created a vibration issue. And so one of my things when I was at Kansas, University of Kansas, University of Louisiana, I was working on floor systems, and there's a lot of vibration issues in floors. And we're trying to make lightweight floors. And so on top of that, that all kind of came together. And so I have a pretty good understanding of the design of buildings for some floor vibrations, like induced vibrations by walking. There's other vibrations I'm not the guy to talk to about, but I get the behavior. And so I used some of that knowledge, right, to help them in assessing those designs. And then they were, you know, working with engineers and other architects, running models, understanding the behavior of the design for walking vibrations, especially when it's a concern. Other places are like on the stairs that they were adding there. Stairs can be horrible vibration problems. There's just not much damping on them. And so stuff.
Yeah, that sounds like our school staircase.
There you go.
It's like vibrating. And then we're like, we trust the engineer that designed it.
Yeah, I mean,
so whatever.
Yeah, you know, so structurally it's probably fine, but service-wise, that's not the most comfortable thing for a client. Mm-hmm. They don't like to have that. And so you know, it's interesting too, though, as you learn about it, right? Serviceability is not it's not an exact science because it's based on human perception, right? And so you may perceive going down the stairs is uncomfortable where somebody else may not, right? Or maybe this one is just totally uncomfortable. I have no idea, right? But like the perception is quite different. Or you might have an expectation that it would be bouncy like this. And so in your head, it's not a big deal, right? But when you're sitting in an office and bouncing up and down, the expectation is there that you are sitting on solid surface, right? And so if you're sitting there bouncing around because somebody's tapping their foot on the other side of the office and creating some sort of vibration that's traveling and transmitting to you and doing that, you know, it is a problem for some people. And so it's really interesting. Like you actually have higher limits for vibrations in like gyms or dance halls because you're expecting that movement. People don't care as much. And so it's just, it's an interesting thing to think about. But so I've done that sort of stuff. And then one of the other cool projects was modeling. I was telling you, I helped model some glass. And it's actually layers of glass and polycarbonate. So they use that for like a bullet resistant kind of glass, right? And do I know anything about bullet resistant glass? No, I don't, right? And do I know anything about the use for it? I mean, other than stopping a bullet, yes, that's all I really know, right? But what I was trying to help understand is why the stresses are developing in the glass due to some of the fabrication and procedures that are involved with these systems. And so I use modeling, right, to help them understand this behavior. And then we actually used our experimental team at our lab in Chicago. So we have quite a large lab in Chicago. I encourage you to look on our website the lab called Janney Technical Center. And they used that information where my models and the data correlated quite well. Like it made sense, you know, it was useful for us in helping that understanding. But the experimental data doesn't show nice, pretty pictures of how the stresses develop and what's going on in the material. Models do. And so with a nicely correlated model that we feel confident in, and these pictures, and you know, these pictures just really are 1,000 words, just like you said, communication for a client. Helps me teach Calc 1 or distribute to the Calc 1 student kind of thing. So yeah, those are just a smattering of projects. There's all sorts of other little projects and big projects that I've been involved in. And I think one of the last really cool ones was right after Hurricane Michael in 2018. I went to Panama City Beach, Florida, and did a bunch of reconnaissance slash just kind of structural help work there, where we're working with a contractor who fixes and repairs things after disasters, and helping them understand the behavior and the performance of certain buildings and elements that are in those buildings that were highly damaged during the storm. I mean, that is something unbelievable to see, the swath of destruction that happens from a strong hurricane hitting a center, like an urban center. I mean, it was just unreal. Like I've seen what tornadoes can do, and they're really crazy, and it's not good. But you know, tornado is typically, you know, mile wide is a massive tornado, right? And like, but this is miles and miles of just garbage and junk everywhere in the streets, buildings, you know, pieces of buildings toppled over, things like that. And so probably one of the most enlightening things about the understanding of behavior of buildings and the, you know, the need to, you know, enforce building codes and making sure that we're keeping up to date with our understanding of building codes and things like that. And keeping on top of engineers who are designing as well, and making sure that they're following these designs and following good practices. So yeah, that's all sorts of different stuff.
It's like a wide range of interesting project you worked on.
Yeah, look, see, that's the point, right? That's where I get back to the basics, right?
Mm-hmm.
Like, you have the basics, it doesn't matter, it's all there, right? You can figure it out. You can figure it out. And so certain companies, for instance, and you know, like WJE will work on, most people will work on a wide range of projects, especially when you're in a, you know, like a branch office, like I am, like a smaller branch office. Like I don't, you know, say to my colleagues like, oh, I'm only, just like you're in a smaller, you know, department, right? You're not going to say to your friend, oh, I'm only going to do this and I'm not going to be part of helping you out. Like, I'm not going to help the team out. And you just don't do that. It just doesn't work out well. And so, you know, by nature of it all, you become, we call it generalist. You know, you become an expert. You dabble in a little bit here, dabble in a little bit there, but you always kind of keep something that's, you know, you always keep your focus on what is, you know, your real interest, and you keep going after projects that are your real interest. But it's always fun too to just like take on these little different projects that and learn about different things. It's interesting and insightful. If you're interested in engineering, I mean, if you have some real drive for it, that's where you're eager to learn about these different things. Yeah.
Thank you.
No problem. Any other questions?
No, it's been a great time. Thank you very much.
No problem.